Hi everyone. Today we're talking about lesson 5-2, talking about multiplying polynomials. So last lesson we learned about the different ways of naming polynomials by their degree and their number of terms, and then we looked at some techniques for adding polynomials together, basically just adding like terms together. Today we're going to move to the next step, which would be multiplying polynomials together. And you've already done this. This is just kind of an expanded version of the distributive property. So we're going to look at some different ways to do that, some different ways to think of it, and look at some examples. So our goal today is just to multiply polynomials together. Our essential question is, how would you go about multiplying 3 polynomials together? And so we'll look at some examples of multiplying 2, and then we'll try to extend that to multiplying 3 polynomials together. So basically this is just the distributive property. Okay, when we look at this, right, we think about the polynomials here, right? We're actually multiplying 2 polynomials. So in this first example, we're multiplying the number 3, which is a constant monomial, and x plus 1, which is a linear binomial. So we're actually multiplying 2 polynomials together, and we know how to do this already. This is just the distributive property. So I'm going to take 3, and I'm going to multiply it by this number, right? Take 3 and multiply it by everything inside the parentheses. So 3 times x gives me 3x. And then 3 times 1 gives me 3. 3x plus 3. Okay. And we can't simplify this anymore. There are no like terms to combine. So we would say that this is simplified. And our result here is a linear binomial. Right? Linear binomial. So second example, pretty much the same thing. We're just multiplying 2, right, the number 2, this constant monomial, times everything inside these parentheses, by everything in that binomial. So 2 times 4x gives me 8x. And then 2 times negative 2 gives me negative 4. Okay, again, I can't combine any like terms. Excuse me. Can't combine any like terms, so we just leave it like that. We look at our next example. So same kind of concept, except for instead of a constant monomial, now we have a linear monomial. So we're multiplying a linear monomial times a linear binomial, but the process is exactly the same. We have x times 2x. Here we have x times x, right? So same basis. We add the exponents. So we have 2x squared. And then x times 5 gives me 5x. Okay. And in this case, we multiplied 2 linear polynomials, right? 2 linear polynomials, and we got a quadratic polynomial. And there's no like terms here, so we can't combine anything, even though these both have x's. This is an x squared, and this is an x to the first, so they're not the same kind of terms, right? This is a quadratic term. This is a linear term. We can't combine those. They're not like terms. And then our last example, here we have a quadratic monomial times a linear binomial. And so here we have 2x squared times x gives us 2x to the third power. And then we have 2x squared times negative 3 gives us negative 6x squared. Okay, so we multiplied a quadratic times a linear polynomial, and we got a cubic polynomial. Okay, so that's kind of the easy example there. It's just an example of the distributive property, but we can take that example and expand it off to higher order polynomials. But for right now, we're going to take a little kind of sidestep here. We're going to look at how to multiply these numbers, right? And you probably learned this in grade school. There's kind of a standard way of doing this. You 12 times 13. And kind of the standard algorithm is we multiply this number times this number. So 3 times 2 gives me 6. And then 3 times 1 gives me 3. And then I put a placeholder, right? I put a placeholder there. And so I'm going to move over 1. And I put 2 times 1 is 2. And then 1 times 1 is 1. And then I add these together. And I get 6, 5, and 1, so 156. Okay, and that works. There's some issues with this algorithm. I think it kind of takes away some of the meaning of the numbers. We're just kind of multiplying these single digit numbers together and not really thinking about this is we're actually multiplying here 3 times 10, right, and 10 times 10 and 10 times 2, and so that gets kind of lost in there, but you know, it works. But there's another way to do this, and it's an area called it's a method called the area method. Okay? You may have seen this before. But what I'm going to do is I have 2-digit numbers. Right? I have 2-digit numbers. And so I'm going to make a 2 by 2 grid. Okay? This is a 2-digit number, so I'm going to put the 2 digits here. And then this is a 2-digit number, and I'm going to put the 2's here. And the way I'm going to write these numbers, so 12, I'm going to write that as 10 plus 2. And then for 13, I'm going to write it as 10 plus 3. Okay, and then what I'm going to do here is I'm just going to multiply all these things together. And I'm going to multiply 10 times 10, so 10 times 10, I'm going to put that answer right here. 10 times 10 is 100. 10 times 2 gives me 20. And then here, 3 times 10 gives me 30. And then 3 times 2 gives me 6. Okay. And then all I have to do is just add these numbers together. And if I look here, I have the hundreds spot, so it's going to be 100. Here I've got 30 plus 20 is 50, so I've got 50, and in the 5 and the 10 spot, and then 6 here in the last spot, so I got 156. So another way of doing that. If you look here, you notice you see some similar numbers. There's a 30, right? There's a 6. There's a 20. There's a 100 there. So it kind of accomplishes the same thing. But what we're really doing is we're taking, you know, the number in the tens position times the number in the tens position, and the number in the ones position times the number in the ones position, and then the tens times the ones, and the ones times the tens, and so we're multiplying all the digits by all the digits. But the advantage of a model like this, or a method like this, is that you don't lose that value of the numbers, right? Here we multiplied 1 times 1 and we got 1, but that doesn't really, it's not really clear that 1 represents 100. Okay? Here it's very clear. We're multiplying not 1 by 1, but we're actually multiplying 10 by 10, and so that's our hundreds number. Okay, so the area model is like that. Now, why are we talking about this? Because we can apply this to multiplying polynomials. So let's take a look at this problem right here, right? So if we were to multiply these two things, right, and remember that x is just represents some number, and so when I add x and 4, I actually get a number, right? And x, again, is just a number. When I multiply by 2 and add 5, I get another number. So I'm just multiplying, in a sense, two numbers together, right? But they're just written weird because we don't know what that value of x is. But I'm going to follow that same process. I'm going to write this as 2x plus 5, so 2x here, plus 5. And then I'm going to write x plus 4. And it doesn't really matter, you know, which one goes where. I could have put 2x plus 5 down the side and x plus 4 along the top. It doesn't really matter. So, but again, I'm just going to kind of fill in this. This is like a kind of like a multiplication table, right? I'm taking x times 2x. So x times 2x gives me 2x squared. And then I have x times 5 gives me 5x. And then I have 2x times 4, that gives me 8x. And then 4 times 5 gives me 20. Okay. So I've multiplied every part of the first number times every part of that second number, right? Every part of the first binomial times every part of the second binomial. And now I could just look here and add up like terms, right? So if I wrote this out, the biggest term here is our quadratic term, or 2x squared. And then we've got 8x and a 5x, so that gives me 13x. And then 4 times 5 is 20. So similar to the last one, right? We had a hundreds place, and we had a tens place, and we had a ones place. Here we have a quadratic term, a linear term and a constant term. Okay, so we're multiplying those two polynomials together. Okay, and also, they call this an area model because if I had, a rectangle that one side was x plus 4 and the other side was length x plus, or 2x plus 5, I could find the area of that by, plugging in x into this equation. Okay, so we call that the area model. There's another method that is probably more widely used or widely discussed, but it's nothing different. It's just using the distributive property, right? And they call this the FOIL method, and I'll explain what that means here in a second. But it basically just means I'm going to take everything in the first polynomial, and I'm going to multiply it by everything in the second polynomial. And where this FOIL comes from is it's just an acronym. It helps you to remember that there's actually 4 things that you have to multiply together here. Okay, so you have to multiply the first items in each polynomial, right? So the first object, or the first terms in every polynomial. So here I would have x times 2x. That would give me 2x squared. And then I have to multiply the outside terms, right? So the one on the left and the one on the far right. So that would be x plus 5. That would give me 5, or x times 5. That would give me 5x. Multiply the inner ones. Okay, so the left one on the first and the right one on the second, the inside ones here. This would be 8x. And then we multiply the last ones together. So we multiply 4 times 5, so the ones at the very end. That can be 20. And then when I combine my like terms, I get 2x squared plus 5x, plus 13x plus 20. Okay, so the first, outside, inside, last. That's what that FOIL stands for. So the first terms in each polynomial, the terms on the outside of each polynomial, and each binomial, the terms on the inside of each binomial, and then the last terms of each binomial. You're going to multiply all 4 of those together. So this is just another way of doing it. This is actually the same problem we just did on the last example, just done in a different way. So this is called the FOIL method versus the area model. And there's not a right way to do it. I mean, there's a couple different ways to do it. There's other models that you can do as well, other ways of thinking about this. But really what this just comes down to is making sure that you multiply all the terms in the first polynomial by all the terms in the second polynomial. So quick story here. When I was in high school and I was learning about the FOIL method, I had a teacher who talked about Mr. FOIL. And so he said, well, this kind of looks like his eyes here, right? And then like here's kind of his hair, and then I was never sure if this was like his nose or if it was a smile or something. Anyway, you can kind of see like a face in there. These are glasses here, right? You got a nose and a smile, and you got a little hat on him if you want, Mr. FOIL. And then, so that was, when I was in high school in the 80s. Now, talking about Mr. FOIL, I was like, well, that's kind of sexist, right? It could be Miss FOIL, it could be like just FOIL, right? It's just, so anyway. So that's a way that I've always remembered it is, kind of looking at that face and remembering it that way. So, all right, so let's look at some examples. So we're going to multiply these polynomials together. And we can do these a number of ways, right? We can use an area model for these, we can use the FOIL method, or we can just say, look, it's just distribution. I'm just going to multiply everything in the first polynomial times everything in the second polynomial. So, so that's kind of the way I think of it. So if I multiply these together, right, the w times the w, that gives me w squared. If I multiply w times 5, that gives me 5w So I've multiplied w times these two things, and now I just need to multiply negative 1. So negative 1 times w gives me negative w, and negative 1 times 5 gives me negative 5. And I combine like terms, I get w squared plus 4w minus 5. If you did an area model, you know, similar sort of thing, work out the same way. I could put w minus 1 and w plus 5. And multiply these together, so I get w times w gives me w squared, w times negative 1 gives me negative w, w times 5 gives me 5w, and w times negative 1 gives me, I'm sorry, 5 times negative 1 gives me negative 5. And then I can combine my like terms, you know, right here, and I end up with the same thing. So kind of two different ways of doing that. Look at the second example. Okay, I'm gonna use the FOIL method just to kind of show how this works. So if I multiply the first ones together, I get x squared. If I multiply the outside ones together, I get negative 2x. If I multiply the inside ones together, I get positive 2x. And when I multiply the outside, or the last ones together, I get negative 4. And when I combine my like terms, well, in this case I get negative 2x and positive 2x, and so that makes 0, so I just end up with x squared minus 4. Now, this is a really common thing. We're going to look at this. This is a special case, and so the reason that this works out is because if you look at our terms, right, in our polynomials, the first terms are the same, but the second terms are opposite each other. And so that creates a special case where those middle terms there, right, the linear terms will actually cancel out, and we end up with x squared minus 4. If I look at x plus 4 squared, now this is an example here that I would say the majority of people kind of mess up on, right? And the reason is because they misuse the properties of exponents, okay? So this doesn't mean x squared plus 4 squared. It's not what that means. It means x plus 4 times x plus 4. Okay, we're multiplying two binomials together. And that's the most common thing that people will do there. They'll say, well, that's x squared plus 16, and it's not. And the reason is because when you just do that, you're not multiplying every term by every other term. Okay, you're missing these inside and outside terms here. So when I multiply these together, I get x times x gives me x squared. X times 4 gives me 4x. 4 times x also gives me 4x. And then 4 times 4 gives me 16. And so I get x squared plus 8x plus 16. The screen's kind of wigging out there, but okay. So notice how different that is. If we just did x squared and 4 squared, we'd be missing that 8x term. Okay, that's a huge difference between those two polynomials. So you got to make sure when you see that, you know, x plus something squared, a polynomial, right? A binomial, trinomial, whatever. It means that thing multiplied by itself. So you got to make sure you're multiplying all those terms together. So you get x squared plus 8x plus 16. One more example here. Here's an example that has two variables in it. Okay. Don't get freaked out by this. We're going to do exactly the same as we always do, and just see what we get. Okay. So here my screen's kind of wigging out again. So here we have x times 2x. That just gives me 2x squared. Okay. Multiply the numbers, add the exponents. And then I have x times negative y. So that's just negative xy. Okay. Don't do anything with the exponents, right? They're not the same base. I'm not adding the exponents. And then I have y times 2x, so that gives me 2xy. And then I have y times negative y, that gives me negative y squared. Okay, multiply the numbers, positive times negative gives me negative, and y times y gives me y squared. So now I'll look here and see if I can combine these like terms. I've still got like terms here in the middle. Okay, I've got these xy terms. So they have the same variables, and the variables have the same exponents, so I can combine these. This is negative 1 plus 2, so I end up with 2x squared. And then I have positive 2xy minus 1xy. That gives me 1xy, and then minus y squared. Right. Same process, right? We just happen to have two variables in this one. Okay, and then our last example, we've been multiplying binomials together. If we look at multiplying a binomial times a trinomial, right? We're multiplying a linear times a quadratic, so we should end up with a cubic, right? First degree and a second degree multiplied together, we should end up with a third degree. So this, we're following the same process. We're multiplying x plus 3, right? We're multiplying x times everything in the second polynomial, and we're multiplying 3 times everything in the second polynomial, and then combining like terms. Okay, it's a little longer process just because there's more multiplications to do, but the process is the same. So 2x squared times x gives me 2x cubed. And then when I have x times negative 3x, that gives me negative 3x squared. And then x times 1 gives me x. Okay, and now I'm going to multiply the second term, right? The second term in that first polynomial. So 3 times 2x squared is going to give me 6x squared. Now, just to make things easier on myself, I'm going to go ahead and line these up. So this is 6x squared. I'm going to write this right below this, so 6x squared. Okay. And then I've got 3 times negative 3x. That gives me negative 9x. And then 3 times 1 just gives me 3. Okay, now I could have just written these out horizontally, and that's not a big deal, but what I did was I tried to line them up so just vertically I can just quickly add those together. So I get 2x cubed, and then 6 minus 3 gives me 3 of the x squareds. Got negative 9 x's and 1 x, so that gives me negative 8x, and then plus 3. Okay, so going the same process, we're just multiplying everything in the first polynomial times everything in the second polynomial. So I have 2 things in the first polynomial, I have 3 things in the second polynomial. I'm going to make 6 multiplications. Okay, if I were to do this as an area model, I would just have to expand my rectangle a little bit. So instead of having a 2 by 2, I would have a 2 by 3. But the process again is exactly the same. Here's x plus 3. Here I would have 2x squared minus 3x plus 1. And I just multiply, just fill out this multiplication table here, right? So x times x squared gives me 2x cubed. X times negative 3x gives me negative 3x squared. Right? You see we get the same numbers, we're just kind of doing it in a different organizational style. 3 times 2x squared gives me 6x squared. 3 times negative 3x gives me negative 9x. And then 3 times 1 gives me 3. Okay. And then when I look at the like terms here, the like terms are kind of on the diagonals here. So here's some like terms here, and here's some like terms here. Right? So that's the way that works out. You end up with the same thing, 2x cubed plus 3x squared minus 8x plus 3. Okay? We're going to name that polynomial. That would be a cubic polynomial with 4 terms. All right. Now our essential question was, how do I multiply 3 polynomials together? Right? How do I multiply 3 polynomials together? Well, the answer is you don't. And I'll show you what I mean by that. X plus 3, I'm just going to make one up. I'm going to use binomials here, but the process would be the same if they were trinomials or polynomials with 4 terms. Let's go, x plus 4. Okay. Yeah. How would I multiply all these 3 things together? Well, I wouldn't. So what I would do is I would multiply 2 of them together first. And so let's say that I'm going to just leave that x plus 3 right there. Okay, I'm just going to set that aside for a second. What I'm actually going to do is I'm going to multiply these two together. So here I have x times x, right, gives me x squared. X times 4 gives me 4x. Negative 2 times x gives me negative 2x. Inside ones, and then the last ones I get negative 8. I would combine like terms here, so this would be x plus 3. And here I'd have x squared plus 2x minus 8. Okay, and then I would just go ahead and multiply those two together. So this is just like we did on the last one. I'm going to multiply everything in the first one times everything in the second one. I can use an area model if I prefer. I'm going to get x cubed plus 2x squared. And then the first times the last one there is going to be negative 8x. I'm going to multiply 3 times x squared. That's going to give me 3x squared. I'm going to write it below there. 3 times 2x gives me 6x. And 3 times negative 8 gives me negative 24. This is an x squared here, right? 3x squared. Okay, and just want to double check, make sure I didn't do anything silly. I got x times x squared is x cubed, x times 2x is 2x squared, negative 8x, 3x squared, 6x, and negative 24. So add these together, I'm going to get x cubed plus 5 of the x squared terms, and then I've got negative 2 x's and minus 24 for my constant. Alright, so how do we multiply together 3 polynomials? Well, we multiply them together 2 at a time. So pick whatever 2 to start with, and the order doesn't matter here. You know, I started with x minus 2 times x plus 4, but I end up multiplying everything in this times everything in all the other ones, and so it doesn't matter. The order doesn't matter. We know that through multiplication, right? 4 times 6 is the same as 6 times 4. The order doesn't matter. Okay, so in your assignment today, they're going to have you do a lot of these multiplications, and there might be some naming questions in there as well, but that's what you're going to be working on. All right, good luck.